Question 21 is a photoelectric question, and the students are investigating. We've seen this sort of picture a million times. Monochromatic, one colour light with a frequency of this onto the sodium plate. Here's the sodium plate there. The apparatus is shown in figure 26. Cool. 27 shows a graph of the relationship between the photocurrent, the current here, I, which is in amps, and the reading on the voltmeter. Yep, nice. Okay. Use the information to calculate the maximum kinetic energy in joules of the photoelectrons. Right, so when they turn their light on, this light here, when they turn it on there, the electrons start jumping. And some of them are at the bottom of the plate and they've got hardly any energy, and some of them are at the top of the plate like this one and they've got lots of energy. Right, so we get this photocurrent. When we turn it on, we get this point up here. As we start turning on this voltage backwards, so we start putting it as a negative voltage, what we do is we start repelling these electrons and they start turning around and not making it all the way. And as they start turning around, as we increase the voltage here, this voltage is increased, we get less and less current because less and less electrons make it across, until finally the most energetic electrons here are stopped by this amount of voltage. Now that voltage that was stopped them, that's how much electron volts those electrons had, the most energetic ones. Alright, use the information on the graph to calculate the maximum kinetic energy in joules of the photoelectrons. So the maximum kinetic energy they had is equal to 1.85 electron volts, and we just have to turn that into joules. So to turn it into joules is 1.85 electron volts times 1.6 by 10 to the minus 19, which gives us 2.96 by 10 to the minus 19 joules. I've got the graph up here again, so it'll help us with this one. Calculate the work function of the sodium. So we've got the kinetic energy max. We've got that, and we want to find work. What's a formula that has kinetic energy max and work in it? Turns out it's kinetic energy max equals hf minus work function. So we'll get our formula down here. Kinetic energy max equals hf minus work function. Add work to both sides, minus kinetic energy from both sides, you get work equals hf minus kinetic energy. That's what we're going to be using, alright? So we'll put our numbers in for that. Work equals hf minus kinetic energy, which equals, what I'm going to do is, because we want the answer in electron volts, I've got the kinetic energy here in electron volts. I'm going to use the H of electron volts as well. So 4.14 by 10 to the minus 15, and from the page before our frequency was, I think it was 1 by 10 to the 15 maybe, minus our kinetic energy 1.85. These two times together, I'm going to times them together first to see what that answer is, and that answer is 4.14 electron volts minus 1.85 electron volts, which gives me 2.29 electron volts. There's my work function. The intensity, which means the brightness of the light, is now reduced and the experiment's repeated. The students obtain a new graph of photocurrent versus voltage. Sketch that new graph in figure 27. Alright, if there's less brightness, the brightness goes down. That means there's less photons, and one electron absorbs one photon. So if there's less photons, there's less electrons. Okay, the ones near the surface that found it the easiest to escape, they're still going to have to be stopped by 1.85. So that's still going to be the same point on the graph. but there's less electrons, and we measure the amount of electrons as the current. So there's going to be less. So we're going to have a graph that looks the same shape, which still goes through 1.85. Make sure it really doesn't cut off before then. 1.85, but then it's just less like that. Right, now they change the light source to one with a different frequency. They observe that the photocurrent is 0 and remains 0 regardless of the sign or the size of the voltage. Explain why this is the case. They've changed the colour, and they've obviously got a colour now that doesn't have as much energy in it, so the electrons can't escape. So I'm going to explain it using the formula. So kinetic energy equals HF minus W. If F goes down, the frequencies decrease. The energy of the photon can be decreased. So that's what's obviously happened. So they must have decreased the frequency. And therefore the photons have less energy. Alright, but they see that no electrons escape at all, so the photons have less energy. In fact, they have less energy than the work function. So in this case, the energy that photons give the electrons is now smaller than the work function. So electrons don't have enough energy to escape.